One last topic area I have for you is around the history of optimization. So it relates to the same kind of thing. You just said that a few years ago you might have stopped. The number of cities that you might have tried to fit
Mhm.
into the traveling salesman problem might have been 50, and
Yeah.
now it's thousands. So can you stretch back a bit further with the history of optimization and tell us why it initially wasn't popular?
Mhm.
Maybe what some of the first use cases were and how that brought us to where we are today.
Like there's sort of two big names. And I have it in front of me so I don't mispronounce it. Kantorovich in 1939, and then George Danzig in 1947. Those were sort of two of the people who really brought linear programming, as I was describing earlier, brought that sort of to the forefront. But Danzig gets a little bit more of credit. He's sort of like the name because he was the person who invented the simplex algorithm, what I was talking about before, going from corner point to corner point in a polygon. But using that algorithm to solve a linear program sort of brought the linear program as an important planning and decision making tool at around that time. So sort of like the um, one of the first applications of that is uh, whenever if you ever go to an OR operations research like site or something that about mathematical optimization and it's like here's our first example. It more or less is going to be something called the diet problem, and that was a very small problem that was developed for I believe the U.S. Army to help um, how can I feed troops? How can I feed like a battalion or something like that? How can I feed that group of individuals, making sure that they have the nutrition that they need, but at minimal cost? So that was sort of one of the original applications of linear programming way back when. Things like and I talk about the integer programming, sort of was developed more or less in the mid 50s. With Danzig and other folks as well who were adding to that. So around that time was when a lot of the initial theory was developed. The problem was once you tried to get past that real simple problem, which was 9 constraints and 77 variables. Um, once you get so that's a very 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 small problem, exceptionally small. Once you get sort of past that, the computational sort of power just did not exist. So fast forward to maybe something like the 70s was when we actually started to get a little bit more of the information or a little bit more of the power to actually solve some of these slightly larger problems that were still relevant to businesses, still relevant, but we actually be able to solve them um, in any type of in any type of speed that would make sense. It's not taking days or weeks or years, but like something that you can actually use. And a lot of these problems were for like oil and gas companies for refineries was sort of one of the original sort of adopters of linear programming, and they were actually uh, very much into funding this type of research in order to push forward the theory and the technology and everything like that. So essentially, what the main bottleneck was computational power, and that is something that is very sort of mirrors a lot of sort of why it took so long for deep learning to also become the powerhouse that it is today, is because for deep learning, the data wasn't there that we needed to exist to really use it, but the computational part wasn't there as well. Enter GPUs, and all of a sudden, boom, this whole new thing sort of just explodes. And that's sort of what mathematical optimization kind of hasn't had just yet. I mean, obviously, I've been talking a lot about how the CPU and performances and all that stuff uh, has really increased over the last 20, 30 years and stuff like that, to have problems that are actually that were they've never been able to be solved. Now they can be solved in minutes and seconds. But just like there wasn't like a new technology that was sort of came on came on the scene to really spur it um, like GPUs did for deep learning. So it sort of just got kind of like lost in the shuffle a little bit. It definitely found its niche. Niche is kind of like too narrow of a word, I guess, but it has early adopters. So I mentioned supply chain a lot. That's sort of one of the big ones that became an early adopter to mathematical optimization and showed a lot of business value there. But then once you get into like the 90s and things like that, where a lot of people started putting effort into the algorithms and really improving that as well. So there's some groundbreaking research that really sped up that part of it, and just sort of uh, adding to that sort of time over time over time, and then uh, Groby um, uh, came on the scene in 2008 from a company, one of our competitors called Cplex, which is owned by IBM. They were, a bunch of people there, including all three of our founders were at Cplex and making awesome advancements from in the LP algorithm space. But then just decided like, hey, we're getting a little bit, you know, uh, slow down. We want to take a different approach, so that's where Gurobi came in. So our three founders decided to start a new company where creating the fastest, most powerful mathematical optimization solver that we possibly can became the top priority. So yeah, there's a lot of early adopters from a theoretical perspective saying this could be really cool. Just the computation stuff wasn't there. It got there a little bit. Oh, people are like, this is kind of nice, but again, let's solve more realistic problems. Again, sort of entered that same bottleneck of computational inefficiency. And now that things have been steadily increasing from people making the algorithms better, for people making the hardware better, again, now we're actually at a point where over the last few years, really seeing businesses solve awesome problems that are at the scale that they need.